Yo, what's up, everybody? Welcome back. Today we are working on our virtual GPU, and today's goal is to draw our first triangle. Context for the project. We are working on a virtual GPU. The idea is that if we implement an entire GPU in software with the hookups to a virtual machine so that we have to write a kernel driver and a user space driver in order to interact with this thing in some way, if we implement all that, we should have a good understanding of how a real GPU would work, right? And then that means that someday in the future, we can design a GPU on an FPGA for fun, essentially, right? What we are working on right now is we have our little test application that runs in our virtual machine that runs some OpenGL code to basically draw a triangle. So if we look at this thing on a existing GPU, not our GPU, we see a triangle that's off the screen because I didn't fix the coordinate normalization, whatever. But we're also seeing the background kind of pulsing green or whatever. If we run this same application with our GPU, we see a flashing green thing, but no, there is no triangle. And the reason for that is because we haven't implemented it yet. Now, triangle rendering in OpenGL is actually quite complex. You have to basically write a generic execution language, I guess, for your GPU. So the idea is that when I write OpenGL, right, there's a 3D thing that I want to draw. This 3D thing has a bunch of points, in 3D space that have some sort of coordinates associated with them. But when I am looking at them as I move my screen around, those points kind of move relative to me, the viewer, but not relative to each other. And so what what people in OpenGL land do is they will write a program that expresses how these things should be changed relative to the current viewport or whatever, right? So what you might do is you might say, I want this thing to look bigger or smaller, and so you might write a program that multiplies the values of each vertex by some number that will adjust its scale. Or you might write a program that adds, something adds 1 to the x-axis of each of these things, and it'll move it over to the left or the right. And for all 3D rendering, all OpenGL calls have to go through this pipeline. Once you have determined where these things are, the pipeline will then run another program that says okay, so there's a triangle here. For each pixel on this triangle, I need to determine what color that is. And so then it will run a program that lets you interpolate some values that you set at each of the 3 corners, and it will give you those interpolated parameters on the triangle, and you can choose what color to make baseline. So if you made this red, green, yellow, you might see something kind of a gradient from red to green, kind of left to right, and red or green to yellow, top to bottom is kind of what you would see. So our simple dummy application that draws a little triangle here, he's going through that whole, oops, wrong one. This one. He's going through that whole pipeline just to say every pixel is going to be white, and I have one triangle, and that's it. So that's kind of what we're working on. We have got to the point now where we have executed a shader for the vertices. So if we look here, it's kind of hard to see, but our program sets up our triangle. Let's see if we can find where that is here. We set up a triangle with these coordinates. Negative 0.5, negative 0.5, 0.5, negative 0.5, 0, 0.5, right? We see that these have been processed through our vertex shader through this program that basically says take the input position, that's a 3D vector, and output is a 4D vector. We are not going to really go into details of why that's done. It's just a mathematical thing that makes it easier to work with. So the expectation of OpenGL is that you export a 4D vector. So we just tack on a 1.0. And we can see that our program output is in fact tacking on a 1.0 here. You see 1.0, 1.0, 1.0 for each of the inputs or anything. Wonderful. So today's topic is going to be going onwards from the vertex shader and trying to get into the fragment shader and say, now that we know where these triangles are, how are we going to display these things? Which means that we're going to have to run this really stupid, simple program that says, hey, take the color 1111 and slap it out to the output color, and that's it. That is the plan for today. So we have been integrating with this library called Mesa. Mesa is an open source OpenGL implementation for a bunch of graphics cards on Linux, and we have kind of hooked in with our own custom thing. We have compiled the vertex shader. He provides like all these callbacks essentially. So like things like create vertex shader, create fragment shader. You make these the active vertex fragment shader. Set like the input parameters to your pipeline call, and then like actually call it. So we should probably be in draw VBO. We know that we've like run our shader. We're not actually running this on the GPU right now since everything is like software anyways. We're kind of testing everything directly in Mesa. So usually the flow would be like GPU lives like over here in like virtual device land, QEMU, right? Then you have like kernel driver that like implements like basically transfer between GPU and here. Then you would have like Mesa down here who knows how to talk to the driver. He sends the shader over, he sends the parameters over, he uploads these to the GPU runs them over here. But since that our GPU is just like completely implemented in software, we have like a lib GPU over here, and usually he would run here, right? But we're kind of just like taking him and like being like, nope, you're gonna sit right here for now, and we're gonna do all our testing like this, and then once we know that it works, then we can kind of move it back over here. So that's why we're seeing like an execution of a shader directly in here. We need to figure out how to hook up the next part of the pipeline, which I have no idea how to do. So I'm assuming that there's some sort of inputs somewhere that we have to handle. Like at some point we said, hey, somebody assigned us some vertex buffers that are the inputs to our vertex shader. And I assume that like somehow someone must give us information about how the output of that is supposed to be used in the fragment shader, but I'm not 100% sure. Also, Fabulous Flow, thanks for the prime, much appreciated. For anyone interested, the term to search here is homogeneous, however you want to say it, coordinates, which is basically match stuff, which makes a bunch of calculations easier to deal with. Yes, thank you for calling that out. That was in regards to the 4-dimensional vector thing, homogeneous coordinates. So I presume, like, do we have anything that talks about, like, fragment shader stuff? There's fragment shader state. Okay. So this will probably define that we're supposed to run on some output of the vertex shader, but how do we know the format of the thing that comes out of the vertex shader? Are we just supposed to assume that they're homogeneous coordinates packed into a buffer? Maybe we, as the GPU writer, get to determine how intermediate stages of our pipeline work. Right, so I was googling like graphics pipeline because I'm a lost is all hell, and in here I saw a picture somewhere. This picture, right? They talk about how there are some hardwired things in here, and like the graphics pipeline will do some sort of like this perspective transformation thing. This is basically the vertex shader. Then he like does some stuff and then feeds that into your pixel shader here. Now, who knows if this is like true for everything, whatever, but this at least reveals that maybe there's some sort of like implicit expectation that the output of your vertex shader is some triangles. Now, if we look at the parameters that Mesa gives us when we compile our thing, if we call like ner debug, because print vertex shader, right? I might have killed a little too early. Okay. We see that this thing talks about inputs and outputs here, right? But what is not clear to me is if the fragment shader has that same thing. So I guess maybe we did like print vs print fs. Maybe that would give us some information about like the fragment shader expectations here. So looks like he has no inputs. Inputs 0. Interesting. Outputs 1. Okay. I wonder then on like the vertex shader side, he has one output GL position, which is like, I understand that in like OpenGL land, GL position is like a special variable. I wonder if our implementation is supposed to kind of tie that back in some way. I wonder. Right? If like stage 0, next stage 4, output's written. Yeah, I wonder if we're supposed to like know that GL position is special. Maybe we can look at another implementation of draw VBO, draw vertex buffer object, I think is what it's called. And maybe that will give us a clue in some way, shape, or form. Maybe we can look for like draw VBO equals and maybe find some other implementation. Like, can we look at like, I don't know, the Intel implementation of this thing? So he has vertex buffers, he sets some indexes, draw VBO. Oh, this does drawing using some sort of like gallium helper function. Yes, GL position is what is fed to the Clipper rasterizer. User outputs are interpolated and passed opaquely to the fragment shader. Yeah, but I want to like what I'm more like a little confused about is like surely the name GL position doesn't exist in graphics card hardware, right? And I actually also don't know if in like if with Vulkan shaders, do they use GL position? Is that like a thing that they use? Behave exactly the same as an OpenGL. Okay. So GL position is like still used, maybe. Maybe that's like a GLSL thing. Maybe the idiot can kind of give me some sort of like clue. This is kind of specified in the GLSL specification. And yes, GL position is explicitly a special variable for vertex shaders. Clipper input in hardware is a hardware concept though, and it's spelled GL position in GLSL. Okay. Okay. If you guys are both saying that, I'll believe you. I'll believe you. So that means that we probably are looking for the vertex shader output GL position, and we need to map that somehow. Somehow. I'll believe that for now. I mean, it seems reasonable for sure, and I just wasn't sure. So I guess somehow we're gonna have to like look at the outputs of the vertex shader. So let's think about this for a second. So that would be on like shader compilation, I guess. So when we compile our shader here, we must have to look at the outputs somehow, which we have done here. We say, hey, we have an output here. And I guess we just need to tell the shader pipeline which output is special, right? So presumably this like ner variable, he has a name. We could just look at the name and see if it's GL position. I expect that it's not what we have to do, but maybe. Index, number members, constant members. Yeah, I mean, name, it could be. It could be that we just look at the name and check if it's GL position. GLSL type. We know we've checked that the type is float vector elements 4. Sampled type, probably not. Has built-in name. Maybe relevant in some way. I'm okay with just looking for GL position for now. I believe it's defined as output index 0 exactly, but I can't remember where that's specified. Ooh. We could look. Built-in variables. GL position is a member of contains the position of the current vertex. So this is GL4 GL position. Okay. In the vertex tessellation evaluation and geometry languages, a single global instance of the GL per vertex name block is available, and its GL position member is an output that receives the homogeneous vertex position. It may be written at any time during shader execution. The value written to GL position will be used by primitive assembly, clipping, calling, and other fixed functionality operations, if present, that operate on primitives after vertex processing has occurred. Okay. In the tessellation control language, GL per vertex named block is used to construct an array. GL out whose GL position members hold the homogeneous blah blah blah. The value is undefined after this. Is also undefined. Tessellation control. Okay. How do we know, like... I think that this would be a NER Mesa thing, if there's a better way to recognize it. That kind of lines up with my gut feeling as well. Also, I see no reason that the user API facing index must necessarily correspond to the Mesa index. Yeah, I agree. Now that you guys are saying it, while I don't actually know, it might also be that you can't even query the index of GL position from the CPU, and user outputs get the entire namespace using start from 0 upward, but not guaranteed. IRC. Yeah, seems reasonable. Seems reasonable because, like, I guess we are in control at like this point of the pipeline, like how we want to represent that thing. So it must be like, let's see if like ChatGPT has a guess. This guy probably, I doubt that he understands the inner workings of NER, but we could check. In Mesa NER, is there a way to check if a shader output is the special variable GL position, which I need to identify to do triangle rasterization? Okay. I mean, this is what I would do. You might want to check its location if you're dealing with... Okay. I mean, who knows if that guy's right? He's a fucking idiot. He doesn't know shit. But that is what I would do. So I think that I will just check the name. So what is happening here for each variable in shader? Right, so we're looking for NER shader out, and I guess we will assert here that mem comp var name and gl position is equal to 0. Is that how mem comp works? We probably want the length as well. I guess we want like stir comp. Man2 stir comp. Man stir comp. Man3. It's man3, I forgot. 0 if they're equal. Yep, so if this assert that these are equal. And then for now, we will just assume that we can only have one output per... This won't pass, because this will only work for the vertex shader. And the fragment shader is going to look very similar. So here we need to do like... This is going to have to change behavior, the inputs and outputs to our shader. This is going to have to change based off of if we're the vertex or fragment shader. Okay, so maybe this will be like Sphero context create vertex shader state. And then we'll say create fragment shader state, which is going to look very similar. So maybe we'll do like, this is create fs state. Okay. And both of these guys are going to call like Sphero compile shader. And we're going to pass in like the template, maybe. Okay. Maybe we pass in the NER shader. And then we do like the input output expectations above. And I guess we kind of pass our libgpu shader here as well. So maybe it's like something like this. So then all of this stuff lives in like Sphero compile shader. Compile shader. And he's going to take in a shader, which is a struct ner shader, as well as a struct lib GPU shader, I guess. And then this stuff just goes away. Okay. Which means that our fragment shader state now, we're kind of assuming now that our fragment shader has a single input. No, we are assuming 0 inputs to the fragment shader, because that's what we got down here somewhere. Fragment shader, 0 inputs. So I guess, can we do like, what is this for each thing? I guess we'll just ignore this for now. So we'll just like assert false here. And we'll say fragment shader inputs unhandled. Okay. Maybe we put this in like one of these. How do you do this? Fragment shader inputs unhandled. I think it's like this. And then for our output, we are expecting one 4-dimensional color vector. I guess. Looks fine to me. And then we compile the shader. Sure. That's like a maybe. Not crazy. So let's build this thing and upload the latest and greatest to our GPU, or sorry, our virtual machine. So turn on networking. Okay, run it. Let's see what happens. Give him a sec. Okay, so here we're saying GL position. He's not passing that assertion. So can we look at why that would be the case? Why is that not working the way I would expect it? Oh, oops, I fucked up. Let me out. Do we restart the VM? I'm tempted. Yeah, let's just do it. What did I forget there? I forgot to type args on the GDB command line. Root. GDB args test app dev dri card 1. Did I spell GL position wrong? That's actually like quite possible. But we will see. Oh, I mean, that's just not... Wait. Yeah, on output it should be. Backtrace doesn't work. That's fucking sick. Breakpoint. Sphero drm winsys.c line 173. And we run again. Let's see. What is he pissed about? 198. Oh, I'm a dumbass. It's not supposed to be named GL position. This would be a GL frag chord. Right? Is GL frag core, or what is it? What did we fucking name this thing? It's not frag chord. It's test app source fragment. GL frag color. Is that special? No. Maybe not. I guess he's expecting one output here, probably. Fragment shader. It would make sense that it can only support one fragment shader. Or one output. Output. User-defined output variables in the fragment shader can only be with the following GLSL types: floats, integers, vectors of the same. They can also be arrays of one of those types. Okay. User-defined outputs from a shader fragment color to represent a series of colors. These color values are directed into specific buffers based off of GL draw buffers state. These are called fragment colors. Jeez. Though you can treat them like arbitrary data. Any fragment color values not written by the fragment shader will have undefined values. Okay. So where do they go? GL draw buffers. I've never seen this call before. Define an array of buffers into which outputs from this fragment shader data will be written. Ah, interesting. Okay. Sure. So we will cover that eventually. That means that like our compilation should not assume anything about the output here. But for now, we will assert that we only handle vec4s. That's fine. And then later, when somebody sets GL draw buffers, we're going to have to figure out how to map that stuff. But for now, we can just not think about it. Okay. We're going to have to bind this fragment shader state eventually. So we're going to do a similar thing here where we set up our fragment shaders like this. Which means that we need to stash the fragment shader somewhere. So we'll just kind of do this. Wonderful. And that means that when we call our draw command, we should have like a fragment shader to run as well. Which kind of makes me think that we should like pass that in here. Kind of hand wavy to like the thing that runs the shader. It kind of feels like he's going to run these things back to back. And he's going to assume, for now, that we have one output GL position. Yeah, that seems fine to me. Which means that in our implementation of this thing, we should do like, we should add this. So can I get out of this like QEMU environment? I don't need to be in here. I want to be in the normal environment. And we're going to go into libgpu and figure out how to like hook this stuff up. I guess we have kind of figured out the fragment shader input. Hand wavy. It's going to be the vertices to GL position. Well, I guess we still don't really know. We still don't really know what the inputs are. If the input's 0, if he has 0 inputs, oh, I guess he actually does have 0 inputs, because usually you would have an input that is like some interpolation of thing between vertices, right? You would normally have like a triangle that is like this, right? And you would have like, I don't know, like a color, right? You'd have like red and green and blue here or something. And then you would like interpolate these values. Because our program is just drawing a constant value, he doesn't have those inputs. In which case, our fragment shader is dumb as bricks. Nice. Okay, so there are no shader inputs other than the code itself. So let's try executing the fragment shader for a single input, right? We'll just pretend. I guess we'll just execute the fragment shader. Yeah. Then eventually we're going to have to figure out where to put the output of that thing. But for now, we can just execute it and see what happens. I like that. I like that. Yeah. So we'll go into libgpu. And we'll go into our header and we'll adjust this to say, we'll call this, instead of execute shader, actually, I kind of feel like this should be like execute pipeline. Execute graphics pipeline, right? And this will take in the vertex shader, len, the fragment shader len, the input definitions for the vertex shader, the data that's coming in for the vertex shader, and then we just like fucking run that shit. Okay. So in the Zig side, we then need to update this to be like libgpu execute graphics pipeline. And he's going to take it in the vs data vs len fs data fs len. Okay. And we're going to, I guess, compile two shaders. We're going to use two compiled shaders here. So this becomes like vertex shader. We execute that thing with our inputs. And then we have some outputs. Our outputs are of the form variable. So an array of variables, sure. Which means that we can kind of like loop over. Fix me, we're gonna like loop over outputs and loop over the outputs and do something with them. Figure out triangles from them, right? But for now, if we're just gonna try to run the fragment shader and see if it like fucking works at all, we can just kind of do this. Boom, 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 boom. Right, so now we have a fragment shader that we should be able to run. So we'll call this the vertex shader executor here. Boom. And then we should be able to make another one of these with the fragment shader. Okay. And we are going to execute this thing with, I guess, 0 inputs. So we'll call this vert outputs here. Frag outputs. And I guess we have like null 0, no inputs. Hand wavy, right? Now, what's a little odd here is our execution function runs for each input, which is kind of weird. We assume that we have, oh no, it's our num indices for output. We're making this many outputs. Okay. Then we say, hey, we have this definition for inputs for this thing. Let me run this once for this, and we will add these inputs. So this should just end, if we make input defs this, and we try to run it once. We have no inputs, and we try to run this thing once. We should get one output here, I think. So let's write down the vertex shader outputs still, and we'll also write down the fragment shader outputs. Sure. That should do something probably somewhat sane. So we're going to execute this. He's going to be like, yep, no inputs, run this thing, no inputs. We're going to get one return from this thing, hopefully. And that should hopefully be a color. That's like a maybe. Not like a guaranteed won't work. Which is about all I could ask for right now, to be honest. We forgot to run the virtual machine. So let's go back to that. We will go here. We will turn on networking so we can upload the latest and greatest. Like this. And then we will run build.sh. And in reality, actually, we probably don't have to update everything every time here, right? We're really only ever modifying the Sphero GPU implementation. So that we can probably save a lot of time here by doing this. Yeah. Okay. So, frag outputs, we get a shader variable with floating point number 1.0. That doesn't feel right to me. It feels like we should be getting a vec4 output. That's kind of my understanding here. So I suspect that when we run, hold on, kill all test apps running in the background. I suspect that this, one of these guys, is not getting translated correctly, right? So we're saying like, I want to load this constant, and we're probably not looking at the extra parameters here. That would be my guess. So can we look at our, can we look at like what we compiled? That might be interesting. So can we go into wherever we like compile the fragment shader? Can we just like look at what we got? Okay. So we have a, we have this. And can we just go like printf to standard error the state len and state data. And then this needs to be an int, I guess. And car star. All right. Let's just see if that tells us anything of interest. Because our compiled shader is just JSON, which is pretty cool for us. Why are we only seeing this once? Oh, because we only did it in the fragment shader. Okay, cool. That was intentional. So it looks like we have a load constants of a F32, which does not match what we saw here. Load constants should not be that. So we've got a bug in our shader compilation where if we see a load constant, I probably should have done this. This fix me that says check if it's actually an F32. We should be doing that. So how do we do that? Load constant instruction. He's got a definition for the output as well as the value. So how do they know in this like print function that it's more than one? That's probably the easiest place to figure out how we're supposed to do this. So can we look at like ner print.c and load, can we just like load const here? Okay, print const from load, ner load const instruction. So here they go from 0 to num components, where this comes from the definition and the bit size. All right. So here we'll assert for now that the bit size is, I assume this should be 32 for now. This comes from load const def bit size. This probably needs to be an arrow. Oh, sorry. This is load const here, like that. Boom. And then what we should do is we should switch here and say if num components, I guess we can switch here. And if we have, one, it's what we were doing before, right? If it's 4, we have to make a new function that's like load constants vec4, we'll call it, and we'll just take in the 4 values. So we'll do something that's like, here's my shader, here's the index of the variable it's going to, and here's our first value, second, third, fourth. Oopsies, right? Boom. Now this thing has to be implemented, but that's okay. And then for anything else, we'll assert false. We'll assert unhandled num components for load const. And then for now, I'm going to actually comment this whole section out to prove to ourselves that this is right? We should crash if we run this now. He's actually pissed off because ner instruction. Yeah, we don't need that. So we're expecting some sort of crashy. Nice, and it's a crashing unhandled num components for load const. Perfect. So now if we set this to 4, we now need to add this load constant vec4 thing. So this is just going to be vec4 with x, y, z, w. Aren't different OpenGL drivers famous for being inconsistent? Yeah, I guess so, huh? I actually don't really know, but I think I have seen some drama, not drama, but like just some stuff around that for sure. Okay, so we want to push this load constant vec4. He's going to be like, I have a x, y, z, w. And now we should be able to be like, I want a vec4 here, not a vec float. And we should be like x, y, z, w. Boom. Nice little C bindings. Simple, simple, simple. Sync build. Build.sh. And we should no longer crash these. Nice. And our fragment shader outputs do, in fact, look sane. Where we have 1, 1, 1, 1. And we can probably even test this, that this is correct, by changing our fragment shader output to be a little bit more crazy. We'll go 0, 1, 0.5, 1. Right, let's get wild out here. We do see 0, 1, 0.5, 1.0. So that's really good. That's really good. I would say that we have executed a fragment shader, for sure. Now, once we have the fragment shader output, we have to run that fragment shader for every single pixel in a triangle, which is something that I haven't really thought about at all yet. So, I guess this lives in the Zig library land, right? That kind of lives in like libgpu. And it should live in like shader pipeline execution, right? So when we say like execute shader pipeline, this function should surely look at the outputs from the vertex shader and group them into threes, assuming that we're in triangle mode, right? So we should for now assert in Mesa that we have triangles. I know that we saw this somewhere. I think it was on draw VBO. I think that we saw the pipe draw info had a Mesa prim mode of triangles, right? So let's start there. So we will assert here that the info mode is equal to Mesa prim triangles, right? So that will make sure that we can assume triangles for now, which means that our graphics pipeline can assume triangles here. So we can say for, oops, this is the test. I want the actual implementation here. So here we can be like for I guess here we want to like assert that vert outputs len over 3 or %3 is equal to 0, right? We want to make sure that we have sets of 3, right? And then we want to do something. I don't know what. I don't know what at all, right? We want to go like, I guess we want to iterate over sets of 3. Triangle index, right? We're going to be like const base is going to be vert, like, is equal to triangle index times 3. And then we're going to go, like, A is going to be vert outputs base. B is base plus 1. C is base plus 2, right? Hand wavy. Hand wavy. And we're, like, can we just, like, iterate the fucking things in this triangle? Oh, it appears that the behavior of regarding GL frag chord, etc., depends on the exact GLSL version. I assume, though, that Mesa's driver backend will abstract that all away for us. I assume that Mesa, for every GLSL version or OpenGL version, will, like, coalesce. Is that the right word? The inputs into the same format. I think that's the right word. Coalesce. Is that a word? To come or grow together into a single mass. Maybe that's not quite right. I guess it's kind of more like convert. Coalesce would be like if I have lots of different versions and we eat them all and we show them all at once. Okay. That's what I get for trying to use big words. So let's just start doing the stupid thing and say for every triangle, we want to just iterate it. So can we do like, we have 3 points. How does this look? I guess we're going to have one that's higher than the others. Right? Hand wavy. And so probably you want to split this thing into 2 triangles. Like this. This is like just kind of like the first thing that's going to mind. Right? You kind of split this into like something like this. Then you can iterate row by row on the triangle. Uh-huh. And then all you need is... Well, if this is like this, though, this would kind of look like this. Which isn't necessarily what we want. I guess this is like... You're splitting the problem in half. Is that even necessary? So you draw one line from here to here. So we'll call this A, B, C. Hand wavy, right? B. You have the line AC, BC. This is like the Y value here, which means you have this as well, right? Just kind of hand wavy, that exists. Okay. Then your left side is going to be defined by the line from A to C, and the right side is going to be defined by A to B. But what if B is on the left? A, B, C, like this. Right? Then you still need to, like... You need to determine which one's smaller, I guess. Okay, so you have, like... some line formula that goes A to C. If it's perfectly flat, it's probably fine. One of these has like divide by 0, right? If you have like y equals equals mx plus b for like a line, I think this falls over if your line is perfectly vertical, right? Because that's an infinite slope, which is a pain in my buttocks for sure. Can you just like interpolate instead? Does that make sense? So you have like A x and B x, and you use the difference between the y values as the interpolator? That seems kind of reasonable. I think that works for a line. So this is going to be like fix me sort ABC by height. But until we get there, we're going to be like for a dot y to b dot y. I guess we kind of want to start at the bottom because we're expecting these to be incrementing numbers. Then the x value is going to be like, in this scenario, c dot y. The interpolation value is like c dot y over y minus c dot y over a dot y minus c dot y, right? This is like the amount of y that we've moved along a y or ca, and then we just interpolate from like c dot x to a dot x. That sounds kind of right to me. Are we rasterizing a triangle? That's the goal. Then on the right side, we're going to go c dot x to b dot x with b instead of a, right? Yeah. Now, these could be flipped. So we're going to call this like x1, x2. And we're going to say left is going to be the minimum of x1 and x2, and right is going to be the maximum of x1, x2. I guess. Then we can go from like for left to right, x. We use our fragment shader output. And we put that somewhere. Right? So we're going to be like out buff. I guess we need an output buffer, huh? This needs to go somewhere. I don't know where yet. For now, we're just gonna, let's hard code a buffer for now. Fix me. This should be a input to the shader pipeline. To probably. But we're just gonna be like, out is going to be like a 1024 by 768. Maybe we could even smaller. 640 by 40. 640 by 480 U32 buffer. Okay. Then we go. These are in normalized coordinates. So we're going to go like out width is equal to 640. Out height is equal to 480. Oops, this gets out width times out height. And we're going to be like out buff at, I guess we can say that this is like, everything here is going to be norm for normalized. Which means that this for loop doesn't work, huh? We can't really for loop like that. So here we kind of want to do sorry, here we'll, I want to do the sort first here. I feel like that's, I just want to get that out of my head. Unstable in place. Source in order with respect to given less than function. Okay, so if we do like, we just want to sort. That's not simple. Not simple. I'll come back to this. I'll come back. Also, we need to assume that these are vec4s. Yeah. We do need to assume that, which means that we need to convert the homogeneous coordinates to like concrete coordinates. So we actually have to do like const a this is going to be like homogeneous. A norm is going to be a vec3 of a norm h0 over a norm h3. Yep. Yeah, it's something like this. So 1, 2. Surely there's going to be some sort of problem with there's going to be some sort of problem with if the homogeneous coordinate is 0, but we can kind of ignore that for now. Let's make a function, a little helper function somewhere that's just like, where does this live? I guess just over here. Function vec homogeneous to vec3. Boom, 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 boom. Let's slap this guy here. This goes like a return of a vec3 of chord. Fix me. What if it's 0? Divide by 0, maybe we call it. And then this guy can be like homogeneous to vec3. I mean, then we can skip this h section here. We could just go like homogeneous to vec3 here. Boom. Okay, cool. I think w equals 0 was used as a hack to discard primitives by some people. I'm not sure if it's guaranteed to work by the spec though, where discard means do not draw. I'll put a note here. RCR and Stun. Dude, put some fucking vowels in your name, dude. Claims that some people use w equals 0 to mean do not draw. So here you could like give it an optional or something. But thinks it's not in spec. Sorry if you don't want your name on there. I can take it out, but I feel like giving credit is better than not. But if you don't want your name in my code base, I would understand that as well. All right, so c.y here is actually c1 to b1. And this is c norm. So we need to go like c pixel. We're going to have to basically convert these to pixel coordinates. So I guess it's going to be like norm to pixel coordinate. Okay. And he's going to take in like a width and a height. And I guess we can ignore depth, huh? Kind of feels that way. So depth will just stay between -1 and 1 for now. And we'll just, maybe this returns like a vec2 even. So we'll go like return vec2. This is going to be like chord 0 over width. Chord 1 over height, right? Kind of hand wavy. And then we need this to be like float from int. This. And I guess we actually kind of want like, is that not what it is? Float from int. Yeah, it is. Must have an unknown typo. I see. As F32. There we go. And I guess we should be actually, instead of a vec2, we should give like a pixel chord. Right? Like this. That kind of seems reasonable to me. Which means that this needs to turn like round int from float. Sure. Fuck it. So now we can go like, give me some pixel coordinates. So we want like norm to pixel chord. B, C. Which means that we can go CPX here to BPX. And then this is going to be CPX0, CPX0, BPX0, APX0, and this is performs linear interpolation between A and B based on T. T supports 0 to 1, but makes these bounds supports floats and vectors of floats. Okay. Does mul add? We need like zig standard lib. Shouldn't that division be a multiplication? Or rather, x plus 1 over 2 times w, y plus 1 over 2 times h. Eclipse place is negative 1 to 1. Yeah, that's a good point, huh? This is negative 1 to 1, huh? So this is plus 1.0 on both of these. Over 2 times. Yeah, you're right. You're right. Thank you. I don't know what I was thinking. It would have become pretty clear that I was wrong eventually, but it's nice for you to get there first. Okay, so we have pixel coordinates here, which means that this lerp now needs like... We kind of want like... This is y pix. And I guess we want like y pix f32. Ugh. So much typecasting, man. Because like the lerp needs... Does this mul add need to be floats? What does this do? Fuse, multiply, add, supports floats and vectors of floats. Yeah, so this, I guess, means that our lerp needs to have everything as floats, which is annoying. We can wrap it though, which makes this a little bit easier. Unless that already exists in the standard library. I wouldn't be shocked if it did. We should check that. Nope. All right. A, B, C. Okay. And this will return back a type of A. Okay, so here will be like as f32a. We need like float from int. As f32 float from int a. Okay, boom, boom. A, B, and then C was already going to be a float, I guess. Okay, cool. I kind of feel like actually we could go further here, where we could get the we want to go like start and val, right? I think we can kind of go further. So then we could kind of auto calculate this. So this is val minus start over n minus start. Yes. So we want like a float here of the first thing over the second thing. Yeah. Yeah. Nice. And then we can go lerp val. That feels pretty good because now we can do like, we can just go lerp int from using everything in pixel coordinates. So A. Am I stupid? This is definitely duplicate values, right? No, it's not. A and B is the value we're lerping, but like according to the y values. So we're interpolating the x values according to the y values. Yes. So we're going to look at y px is the value. So the start is c px1. The end value is a px1. And the value is y pix. Boom. Cool. And then x2 norm is the exact same thing, but replace a with b. Looking good. And then this is no longer x1 norm. This is x1 px and x2 px. Which means that we need like an int from float here. Okay. Okay, pix. Left, right. X pix. All right, we got there. So we should be able to now look at like outbuff at y times width plus x pix. So y pix times outwidth plus x pix is equal to the output of the fragment shader. So we have like frag outputs. Can we do like, we need to convert this somewhere. So frag output, frag color U32 is going to be like 0. We're going to have like frag outputs 0, vec for 0. This is going to be the red value. So we're going to go times 255 int from float. Frag color U32 or equals this. Right? And then we're going to go, this gets shifted left by 8, 16, 32. I think that makes sense, right? So we have like RGBA in like vec4. Then we turn this into like a U32 RGBA value. I think that's right. Probably. I don't fucking know, man. We'll see. We'll get there eventually. Okay. So like maybe, now we also have to do some bounds checking here, right? So this triangle could easily be out of bounds of the thing. So here we should assume that like the left value should be the maximum of this or 0, right? So if 0 is bigger than what we get, then like get the fuck out. And then here we should take the minimum of this thing and the right edge. Okay. Cool. Then the y bounds should be the same. Alta 4, thanks for the raid. What's up, everybody? Welcome back. I hope you guys had a good stream over there. We are working on a virtual GPU. So the idea here is that we are creating a fake PCI device in a virtual machine that acts as a graphics card and implementing the graphics stack to go alongside it. So that's like a kernel driver that passes messages over PCI to the thing, as well as like a Mesa OpenGL implementation that will take like commands that are compiled from Mesa and like feed them to our driver, and then we use our kernel driver to do what we need to do. We are in the progress of implementing shader running, compilation and running. So for those of you who are new to like 3D graphics programming in general, typically what happens is you have like a 3D object who has a bunch of vertices, right? When you like do something like in Blender, I scale up this thing up and down. What is happening is on the GPU, we are saying, hey, GPU, for every vertex on this cube, could you like multiply the value of this thing by 2 or 1 or 3, right? This is like a program that runs on the GPU that is like totally in the control of the developer. So what happens is that gets fed into Mesa, the OpenGL implementation. He compiles that into some intermediate representation, and that intermediate representation is then fed to us, and we can do whatever we want with it. So we have made like an instruction set, which is just like we made like a JSON blob of a bunch of commands that we can run. And we are currently trying to implement the second half of this. So we explained the vertex shader just now, but there's also the thing called the fragment shader that says, given a one triangle, for every pixel in this triangle, what color should it be? So we have run both of these shaders, we have like the correct output, and now we are currently trying to figure out how to walk the triangles that have come out and actually put the correct colors in that thing. So we're working on like triangle rasterization right now in software. That's what you're watching. Apologies for the brief intro. I hope that that is not completely over your heads. I know that I'm not doing a very good job explaining because I've explained it like 4 times a day. So I'm just, we're getting less and less detailed on each one. But I hope that you guys enjoy this day. Thank you again, Alt F4 for the raid. Shouldn't you just sim out the loop iteration if the pixel is out of buffer and not draw a pixel at the edge? Skip. Shouldn't you just skip the loop iteration if the pixel is out of the buffer? Yeah, I agree. But that's kind of what we're doing. We will do that here. We haven't got there yet. So if here, I guess we want to set if ypx is less than 0, get the fuck out. Or is it this in this language or in this language? I think it's or in this language. Ypx is greater than or equal to the height. Get the fuck out. Continue. Okay. Now, really, we could like clamp it here. Right? Like this is kind of stupid. Should just set bounds correctly. So you're running your own virtual PC, which is using that virtual GPU. We are integrating with an existing virtual PC. So we have taken the QEMU source code and we have added a device driver for it. So we have like a PCI card that we've implemented using QEMU's framework, which is a lot easier than doing it ourselves. In the same way that we've written a Linux driver instead of writing an operating system for ourselves. There's like I would give this like a 30% chance of working once we get it compiling. This seems like it might do the right thing. We will need to like visualize the output of this thing in some way to see if we got it right. So let's start, I guess, by mem setting this thing to 0. So it'll be completely dark. Int from float is mad because this thing probably needs to say that I'm an F32 or U32. And then these guys need like as U32s here, I guess, which is annoying. So much typecasting, man, but it's kind of like the benefit and drawback of Zig at the same time. Is like you want the explicitness because it stops you from writing bugs, but it's annoying because it's a problem. Spherophoria, X2 pix, forgot to replace another A pix with B pix. Yeah. Good eye, thank you. Thank you. You are correct. Okay. We do need to sort these things by height. That is what we said. We said we were going to draw our triangles by essentially splitting it into 2 halves, right? The top half and the bottom half. And then we are going to iterate like basically from the left side of a lerp on this line to the right side of a lerp on this side. Linear interpolation, sorry. Now, for that to work, these need to be in sorted order. So I guess what we'll do is we'll say what, like there's like a sort function in Zig, right? It's in like stud mem sort. Sure. So we want to take like these 3 things, and I guess we will kind of start them as an array. So we'll say like var pixels or chords. is going to be an array of these three things. Right? So there's going to be like three vec3s. Oops, it's like this. 3 vec3, boom. And we're going to be like, sort these, please. So presumably we take in chords as well as the fact that we are sorting vec3s. The items are the coordinates. Nice. The context is going to be null, or I think void maybe makes more sense. And then we need a less than function. So in this language, you cheat by if you want inline functions, you have to make an inline structure and then make a function in that thing, which is kind of funny. But you know, it is what it is. He wants arguments of context, which is void for us because we don't give a shit, and then we have left and right. So LHS is a vec3 and RHS is also a vec3. Okay, so how do we determine? We are sorting by height, so we're trying to get them in increase it. We want A to be the highest up is kind of what we've drawn here. So we want we want these to be sorted in ascending order, we need to do RHS is less than LHS. And we're looking at the Y coordinate. Sure. And is that Zig latest or 0.13 dev? I'm on 0.13, I believe. I'm whatever's in like the Nix repos at the time of writing. So 0.13. Oh no, wait, I'm using, that's a lie. I fucking lied. I import a tarball for the latest package of Zig 0.13. Fuck, I just closed so much stuff by mistake. God damn it. It's okay, we're fine. Okay, so these things should now be sorted. So now we can do like const A pix is equal to chords 0, B is 1, and C is 2 after sorting. And now we just do this same thing again, I guess, for B to A. So we're gonna look at B. Okay, let's kind of look at this picture again. So the left side is still going to be determined by the lerp of C to A, but the right side is no longer going to be C to B, it's going to be B to A. Yes. I think that makes sense. Otherwise, this is all the same. Fix me, big dupe. Does 0.13 not have destructuring? I don't know. Does it? I didn't know Zig had destructuring at all. I've never seen this in my life. Is this like a thing that exists? Is there like a merged thing here? Do we need the feature? Proposal here. Const A, const B equals array. Oh, interesting. I didn't know that. So you're saying I can do like const A pix, const B pix, const C pix is equal to chords. I've never seen that in my life. That's pretty cool. I'm a fan. Okay, so this right shift by 32 is stupid. That should be, or left shift, which should be 24. Okay, we forgot to set the width and height in these things here. Okay, what else? He's mad that 615. He wants a pixel chord. Right, that's true. That's a pretty good point. Which means that this less than probably wants a pixel chord as well. Chords expected this, found that, because here I'm supposed to write pixel cord. Oopsie doopsies. There we go, much better. Okay, so that built, which is pretty good, which means that like we can maybe run this thing. We accidentally closed the VM, so we'll have to pop that thing back up. And let's just like kind of like see what happens. So we're not expecting anything to show up on the screen right now. We are just kind of expecting that nothing crashes. That's kind of like the big win for us right now. So let's build and upload the latest and greatest over here, and let's just kind of hope for the best. Okay, so we did just panic. That is not surprising that much. So can we like GDB test app dev dri card 1. Boom. Run. Okay, so like what's he complaining about? It's in 412. No, sorry. 605. In the fucking other one. Here. Whoa, really? So in shader.zig 605, sorry. We have the wrong number of vertices. That's surprising. Surprising. So can we like look at that? So that's frame 19. P vert outputs. Len is 7. Oh, I'm just an idiot. That's true. We're just fucking stupid. So our test app, we added a few extra variables or a few extra vertices to our triangle the other day, just to like prove that our vertex shader was working, and it's just not a multiple of 3. So let's just fix that. 1, 2, 3, 4, 5, 6, 7. Yeah, I mean that is in fact the case. All right. So zig build and copy the latest and greatest over. Quit this really quick. All right, wait, so that's good. We aren't crashing. Are not crashing. Question, what would you say as someone who writes a lot of Rust? Why would I like Zig? That's not like a loaded Zig question. I'm generally curious. I don't know it that deep. Okay, so I always say this, and then somebody linked me a tweet by the creator of Zig that says that I'm a fucking idiot. But I'm going to say it anyways. I think that if you were to take C++ and look at like what you think it should be, I kind of think that Rust kind of fits that narrative pretty well, right? Like we're not talking about like early C++, right? We're talking about like modern C++, right? Like what the standard library is like giving you C++ 14 if you use like std, algo, and all that shit, and like templated programming and like interfaces. You use all those things heavily. Rust is like a better version of that. Now, when you think about like Rust and C++, I think that you end up with a lot of like complexity, right? Like the idea of like movement of values is complex, right? So like in C++, you end up with this like rule of 5 shit where you have like move constructors and copy constructors, and like you have to deal with like RAII or like drop traits in Rust or whatever, right? Like the idea that like things like kind of happen for you, but you like encapsulate these nice, tight, like hard to break objects. I think that's like that really like fits the Rust model for me, right? You just like do whatever you can to like prevent somebody who's using your code from fucking up. Hand wavy, right? Which is like a really noble goal, but it comes with a lot of like restrictions, right? They prevent you from making mistakes by really preventing anything real. Like so it makes like in my mind a lot of like Rust refactoring and stuff like very painful. Working in Rust can be like frustrating, but you work through that frustration the first time you compile it, like it usually works, is like my experience with Rust at least. Zig is like if you took C and you gave it the same treatment in my view, right? So you still have a lot of like the improvements that we've learned over like the past 20 years of like maybe implicit typecasting is like kind of a problem, or like maybe we should have behavior that the optimizer can exploit, but maybe we can be a little bit safer about how we handle the failure cases of that, right? So like it's very like simple. They don't have like private variables. They don't have like drop traits. They don't really have like traits at all. It's like you just kind of like can do what you want. What the language doesn't really do anything that you don't expect, but it provides some niceties that kind of make it better to work in than C. So that's kind of like the naive way to say that is I would say that like Rust is to C++ as Zig is to C, but the creator of Zig would disagree with that according to that tweet someone sent me because he's like, I made Zig to replace C++. But it's like, I would classify C++ as like a bad C++. Like, you know what I mean? Where like Zig is like very much more like clean. I don't know how to say it. I hope that answered in some way, shape, or form. Kind of like rambly, but those are my thoughts. Okay. So let's get back into libgpu and let's see if we can actually like look at the triangle we drew. That'd be kind of cool, right? So we're not actually hooked up to like the correct spot right now. We're kind of running this like in our OpenGL user space driver because we can, because our GPU doesn't actually exist. But we should be able to just like yoinkies an image rendering library and use that to do what we want. So can we just like curl-o this thing? And then I wanted to use it for Vorpal, but couldn't find much grcp support for it. Yeah, I would. I mean, my knowledge on this is very limited, but I don't think that you're like sitting on top of like a giant crate ecosystem like Rust. But also, I haven't looked. I have just been like, the nice thing about Zig is that its C interop is like very good, like very painless in the happy path. So like you can leverage a lot of C libraries very easily, and like the Zig model fits very well with the C model. So it's like not like in Rust where you have to create these like wrapper structs and stuff, and like implement dref for all of them and stuff. It just kind of like works, but it does mean that you have like, it does mean that you would use C APIs a little bit more directly, which is maybe fine. Okay, what am I looking at? I am trying to render an image. I forgot. So we were trying to pull in STB image, which means that we need to define the implementation and then include it. So that gives us all of the function definitions. We just need to make sure that this file is used in our library. So we say lib add c source file, which comes from file equals b path source stb image.c. Then, oh, we want stb image right, actually. I forgot. Wrong one. Wrong one. We want the one that lets us write images, not the one that lets us read images. Oopsies. So let's go curl-o this and fuck stb image. We want stb image right, which means that in here we actually want this definition. And then this is fine. We probably want like lib add include directory of b path source stb, or just source, I think, actually. Okay. And then that means that if we want to use the image writer, we should be able to go in here and go like const stb image is import C import, I guess. C include stb image right.hk. Which means that in here we have like outbuff. No, this is in the wrong folder file. You want this in the shader. Shader file. We should be able to be like stbi, like write a PNG with a file name. width. So width comes from out width, height comes from out height. He wants comp. I think comp is compression or components. Probably components. 4 bytes per pixel. 4 bytes per pixel, and then we want data, which is out buff pointer, and the stride in bytes is going to be out width times 4. I think that's right, but who fucking knows? Let's see if that at least compiles. He's mad because stblib not found, which means that we have to link libc, which I thought we already did, but maybe that was in another branch. And then he's mad that pointer doesn't exist because it's true. It does not exist. It's not a slice. It's an array, which means that we put an ampersand. Oopsies. And then we just kind of will ignore the error for now. All right, so that compiled shockingly. Let's see if it actually generates some images for us. Okay, that looks promising because it's slow as shit. So, and we do have a test.png ping here. So can we scp root at localhost test.png here. That's something. For sure. For sure that's something. Now, it's upside down, which makes sense. It's upside down. It's also, I don't think, in the right coordinate space. I'm pretty sure that this thing is supposed to, like, because when we draw this using, when we run our app using the existing GPU driver, not the one we wrote, but the existing one, this is what we see. So the triangle is the right color, for sure. The background is not, but that makes sense because the GL clear is actually not getting executed there. And then I think that because we memset as 0, the alpha channel is 0 as well. So can we try to draw this on a black background for now? So can we do this should be RGBA. So 0xFF 1, 2, 3. Let's see if that should make the background black. Why is he mad? Oh, because we accidentally closed the fucking virtual machine. God damn it. I keep doing that. That's pretty fucking sick. Like, I delayed my excitement a little bit because I was trying to diagnose why it was wrong, but like, that's fucking sick. Like, that we have implemented like a full vertex fragment shader run. It's not perfect by any shape, maybe like by any means, but that's fucking awesome. Like, that's so cool. Okay, kill all test app. Okay, so SCP, this thing back here. There we go. Okay, sick. So we need to flip it, and we need to fix our coordinate normalization. So unless it's wrong here, like why is it wrong? I actually don't understand why it's going off the edge in the first place. Can we look at test app here? Do I have this open? No, okay. I don't know why it's getting mad at me, but whatever. So we set a viewport of width by height, which is 1024 by 768. And we set the vertices to be negative 0.5, negative 0.5, 0.5, 0, negative 0.5. So everything here should be, like, nothing should be past 1.0. So I suspect what's actually happening here is that the viewport size, I suspect that we are not using the right viewport size on the, oopsies, OpenGL driver, or on the, like, correct working driver. I suspect. So resizing this doesn't change anything. I would be curious to know what the resolution of this display is. So can we print that in our test app where we pick a preferred mode? Can we print out the size that we're using? Because I think we just kind of fucked this up, where we're supposed to get the width and height from the mode. So let me look for preferred mode. This thing gives us a mode info, which has a H display and V display. Can we just like print preferred mode has this by this? So preferred mode dot H display, preferred mode V display. I suspect that these just don't match. That'd be kind of cool. Oops, I forgot to put a little dot squiggle. Can we... Hold on. Test app dev DRI card 0. Yeah, preferred mode has 601 by 466. So that makes sense, actually. So I believe, actually, that means that this is correct, right? The triangle should be centered on the center of the screen, which it is. And it's just that in the, when we use this guy, we are drawing to a texture that is just way larger than the actual viewport is. So I think that's fine. I'm actually not worried about that at all, which means that this is working correctly. That is a weird resolution. Yeah, I don't know what the fuck is going on there. I'm not going to think about it. And so what is the next step here? The next step, I guess, is to... Sorry, let's just look at what we have here. libgpu. Shader zig. I guess we could try a couple other... We could try drawing several triangles here. Let's just try... Yeah, let's try a couple more triangles. So let's go back to our test app. And... we can just kind of do something that's like... Let's draw from like... I want something that's like kind of like skewed a little bit. So let's do... Can we just rotate it a little bit? Yeah, so let's put the point on like the right side. So we'll go... X is going to be like negative 0.5 to 0.5. And then the Y is going to be... The first one is going to be up. Second one's going to be bit down. And the third one's going to be right. And then can we just like kind of like add 0.2 to all of these things so that it's kind of like shifted a little bit? I just want to see what happens if we draw that. Okay. So SCP the thing back. That's not good. That's not good at all. I was expecting to see two triangles. What happens if we comment out this? Okay. So we'll go kill all test app. Oh, it's actually fine. It's I forgot to change this from 3 to 6 down here. Oopsies. That explains it. It's hard to check if you're like, am I wrong because I'm OpenGL, or is it wrong because my GPU driver's wrong? Okay, yeah, there we go. That's working like I expected, right? So one triangle here, one triangle here. That's pretty sick. That's pretty sick. And then can we try drawing one that's kind of like off the screen a little bit? So let's kind of like add 0.6 to this or something. So kind of push it too far to the right. And look at this. Oh, did we not SCP it back? No, we didn't. Okay, so it looks like the clipping on the right side is working correctly too, which is pretty sick. Okay. Yeah, I'm really happy with that. Really happy with that. That's super fucking cool. So I think that we can say that we've run a full OpenGL pipeline. Now we have to hook it up to the GPU correctly still, but I think I'll leave that as like a happy hour exercise. I don't think it's really that interesting. Like the only things that we have to do to get this to actually run like within like this screen is we have to basically copy all of like the compiled vertex shader and fragment shader over to the GPU as well as the vertex buffer. But I don't think we've kind of like covered everything that we would need to do that on stream already, right? We've looked at M mapping buffers, so we can just like copy the vertex data over with an M map, like we did in the frame buffer stream. Same with the compiled vertex and fragment shaders. Like all three of those things just get like M mapped to GPU resources. So I'll probably do a happy hour of that tomorrow. And then I think that probably not tomorrow. Tomorrow I can't stream. So Monday I'll probably do that, and then Tuesday I think that we'll try to like upgrade to start doing like more complex shaders, right? It would be really cool to get like an actual 3D rendered thing. But I'm like super fucking stoked on this. Like it's insane that it works. Yeah, it's crazy. So thank you for watching, guys. This has been like a month of work leading up to this. So exciting to see something actually fucking start to come together. If you like what you saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. It is 3:45 Pacific time now, so anywhere between like 3 hours ago to now is when you should expect to see me live. 12:30 to 2, we usually do, or like the first half of the stream, we usually do what we call happy hour, which is like kind of supplemental content where we're kind of like cleaning stuff up, working on like smaller tasks or things that don't deserve their own YouTube videos. If you want to see those and you're watching on YouTube, they are under Patreon or YouTube member streams. Or sorry, VODs, I guess. If you want to see archives of what we were seeing right now, we have playlists on YouTube organized by project. So right now we're working on like this I want to make a GPU project, but there's all sorts of other stuff there if you want to check that out. There's a link in the Twitch description. Code for this should end up on GitHub under the GPU testing environment repo. So check that out if you want to see it. There's a Discord link in the Twitch description if you want to get notifications of when I'm going live or talk about shit off stream. Otherwise, I think that is the plug sesh done, and let's find someone to raid on Twitch, YouTube. Goodbye.